All right, folks. So this is the correlation and linear regression pre-lab. And as always, I sent out the R Markdown document to follow along with the pre-lab in a Canvas announcement. You'd need to download it onto your computer and upload it to RStudio Cloud. And I'd recommend putting it in the pre-labs folder. If you need a reminder on how to do that, look at the beginning of the categorical variables lab, and I put a link to that in my Canvas announcement as well. So we're going to start, like always, we're going to load the packages we use. So we've got the tidyverse package, and we've got library infer. Click the play button to get those to load. And then we need to load in my example data. So as always, it's GSS, then the assignment operator, which is the last sign and the dash, read underscore CSV, parentheses, and then quotation marks. And then my recommendation is to hit tab into that data folder, and then tab to GSS clean. And then if I press play, it should show up in my environment, and I could click on it to see the spreadsheet-like version. So as we've been doing for the past couple weeks, we're going to be doing exploratory data analysis. So we're going to do some data visualization, and then we're going to do some statistics. This week, we're thinking about the relationship between two quantitative variables. So the main data visualization for two quantitative variables is a scatter plot, and we're still going to be using that ggplot function, but then we need to add a geom. And this week's geom is a geom point. So it's not geom scatterplot, which is maybe what would make sense, but it's telling what the geometric object we want, and we want each of our data points to be represented as a point. So I'm going to do a ggplot of GSS plus a geom underscore point, parentheses, and then inside there I'm going to need an AES, and then inside the AES I can specify my X and Y variables. And I'm going to have both of them this time because I have two quantitative variables. In this case, I'm going to try and predict a person's highest year of school completed based on how much school their spouse has completed. So traditionally we would put our response variable, the thing we're interested in, on the y-axis, and then we'd put our predictor variable on the x-axis. So my y is going to be equal to highest year of school completed, and my x is going to be equal to highest year school completed spouse. I think in my code here I put the X first and then the Y. It doesn't matter which one you put as long as you put the X and Y correctly. So the Y should be the thing we're interested in predicting. And now I could run that code and look at my scatter plot. So just like last week, we're going to get this warning message about data points that have missing values. That just means either someone's highest year of school completed or their highest year of school completed for their spouse is missing. And it's a lot of missing data, right? It's 1,361 rows out of my total 2,348 rows. But maybe we're just going to proceed anyway. We want to try and find a descriptive relationship between these two variables. So one question is if this plot shows a positive association, a negative association, or no association, and then if it shows an association, how strong we think it is. So you could think about that for a second, what your guess might be. I would say this is a positive association because I see it going up over time, or up over the course of the plot. Association. And I would say it is moderately strong. It's not super strong, super linear, but it's not kind of all over the place either. I would say this is kind of moderate, but that's an opinion question. All right, so that's our data visualization for two quantitative variables. And now we're going to do some summary statistics or some statistical techniques to quantify the strength and direction of that relationship. So one thing we could do is find the correlation between the two variables using the core function. And we would put that inside our summarize in our data pipeline. So I would say GSS, that's my data set, then summarize. And inside that summarize, I'm going to say the correlation is equal to COR. COR is the function that finds the correlation, where my Y is the highest year of school completed, and my X is the highest year of school completed spouse. So if I hit play on that, it gives me an NA. So this is just like we found last week when we were doing our summary statistics and we got a bunch of NAs for our summary values. R is going to give you an NA for any summary statistic if there are any NAs in your data. So there's a couple approaches to how you could fix this, but one of them is just to put a drop NA into your data pipeline. In this case, I need to drop NAs on both my highest year of school completed variable and my highest year of school completed spouse, because there could be NAs in either one of them. So I just stick that into my data pipeline, GSS, then drop NA, then, so I'm using the pipe to continue my pipeline, then I'm going to do that same summarize. And if I hit the play button on this, now it says the correlation is 0.596. So the correlation is 0.596. And you could try and assess whether you think that's a strong correlation. I think it's usually considered moderate because the largest correlation would be 1 and the smallest is 0. This is kind of in the middle, but that again is a judgment call. And then another way to study the relationship between two quantitative variables is to find a linear model. So R has this function that will do least squares regression and find the equation of the linear model for you. It's called LM, which is short for linear model. And LM is one of the few things where you can't do it in a bunch of different syntaxes. The only way to do LM is using the formula syntax, which is the one that I'm teaching in the other section. So we have to do a little bit of that in this class. And the way that it works is you write Y tilde X. So you use the response variable tilde your explanatory variable. And the thing in the middle, it's like a squiggly line. It's the tilde. On my keyboard, it's above the tab key, but below the escape key. And I think I have to do like shift and then hit that key in order to get the tilde. You could also just copy it. If you can't find it on your keyboard, you could copy it from my pre-lab. And so the easiest way to get the linear model is just to do LM parentheses. Then you put in your Y variable, what you want to predict, which in this case is the highest year of school completed, and then the tilde, and then the predictor variable, the explanatory variable, highest year of school completed spouse, and then say data equals GSS. So this is a little bit different syntax than we've seen before, but I think that you will be able to follow along. And if I hit play, then I'm going to get out a little bit of information. So I get the call, so this is sort of what I put in, and then I get the coefficients. So it gives me my intercept coefficient, 5.847, and then it'll give me my slope coefficient, my B1 value, and it's labeled based on the variable that is my explanatory variable. So this is my slope value, but instead of saying slope, it says the name of the variable that it's associated with. So that's one way to just run a model and get the coefficients. It's a little bit better practice to give your model a name so that you can refer back to it later. And in order to do that, we need to use the assignment operator. That's the little less than and then the dash. And you can put whatever you want in front of the less than and the dash to make a name. It has to start with a letter. It can't start with a number. It can't have spaces in it. But basically, you could call it whatever you wanted. You could call it your first name, like I could call my model Amelia. I usually use these kind of dumb names where I start with M1, that's my first model, and then I'll call my second model M2, M3, M4. You could think of a smarter name for your model. You could call it like school model or something like that. So this is kind of a do what I say, not what I do. but this is how I usually do it. So I'm going to say M1 gets with the assignment operator, and then this whole LM code again. And if I hit the play button, nothing prints out, but I get a new object over here in my environment. I get an object called M1. If you click on it, this is not a super useful thing. It's not like a data set, so I usually don't recommend clicking on it. So what's more useful than just clicking on it is to look at the summary. So we can take our model object, it's sort of like a little data set, and then pipe it into the summary. And if we do that, we get a much bigger table of information. So it has a bunch of extra stuff. It's still got the call, but now it's got things about the residuals. At the bottom, it has things about the residual standard error and the R squared. We're going to come back to a lot of this when we wrap back around to regression at the end of the semester. But for right now, the most useful stuff is in this estimate column. So we've got our intercept, which again, it's 5.847, and our slope, 0.594. It's not labeled slope, it's labeled whatever the name of our x variable was, but that is what it means. And so one thing that we might want to do is write out the equation of our model. And I would probably write it out, y hat is equal to the intercept, 5.847, plus the slope, 0.594, times, and then it's going to be this x variable. I'll just copy paste it so that I can see it there. So that would be the equation of the line. It's got the slope and it's got the intercept. One thing that you want to do if you have found a model is you want to interpret your coefficients. I have some generic sentences that I like that just have blanks that you can fill in, and it's totally fine to just copy my sentence and fill in the blanks. You don't have to get creative about it. So the sentence that I like for the intercept is if the value of explanatory variable was 0, our model would predict response variable to be intercept value. So let's see, I'm going to make this my full screen so that I can see my equation and these sentences at the same time. And I'm just going to copy this intercept sentence. So if the value of explanatory variable, and this is the highest year of school completed by your spouse, was 0, they didn't go to any school, our model would predict the response variable, highest year of school an individual completed, to be, and then it's the intercept value. So that 5.847 or about 6 years. I'm just rounding. So if your spouse hadn't gone to any school, this model would predict that you went to about 6 years of school. So that's just plugging in 0 for the highest year of school completed spouse. That makes this term go to 0, and then that's what our y hat value would be. So it's not always useful or interesting or reasonable to interpret the intercept. You have to make sure that 0 is a reasonable value that that x value could take on. And in this case, it actually is. We do have a few people whose spouse went to no years of school, but sometimes 0 is way outside the range of the data, and so then we shouldn't actually interpret the intercept. So usually the intercept is the less interesting one to interpret, and the thing we really want to interpret is the slope. So let's do that. So my generic sentence is, for a 1 unit increase in explanatory variable, our model would predict, or we would expect, or on average, you need some kind of hedging your bets because it's not going to be an exact relationship, but our model would predict a slope value unit increase or decrease in the response variable. So again, I'm just going to copy this and then paste it, and then let's edit it. So for a 1, and then we need to figure out what the units are. So it's the units of the explanatory variable. In this case, it's years. So for a 1 year increase in the number of years of school completed by your spouse, our model would predict and then we plug in the slope value, 0.594, and we have to think about the units for the response variable, and they're also years here. So year, we have to decide if it's an increase or a decrease, and in this case it's an increase because it's a positive coefficient, so I'll just say increase. And then we plug in the response variable, the number of years of school an individual completed. So for a 1-year increase in the number of years of school your spouse completed, our model would predict a 0.594 year increase in the number of years of school you completed. So it kind of goes up. It's not a 1-to-1, but it kind of goes up a little bit for every year increase in school completed by your spouse. Another thing that we might want to do is make a prediction based on our model. So there's more programmatic ways to do prediction, and we'll get to that later in the semester. But for now, I just recommend you use R, like a calculator. So let's see what the model would predict for someone whose spouse completed 12 years of school. So I'm just going to go grab this because that was my model equation, and then I'm going to put it down here in this code chunk. And so I've got my intercept, I've got my slope, times, and then I need to plug in for the highest year of school completed for the spouse. I'm going to plug in 12 years and hit the play button. So if your spouse completed 12 years of school, our model would predict you completed 12.975, which is about 13 years of school. Does that make sense? Yeah, probably people marry people who have gone to about the same amount of school. And we can see that's not exactly true, right? So for people whose spouses did about 12 years of school, I think that would be like here on my x-axis. I can see some people had only done maybe 6 years of school, and other people had done 20 years of school. So there's a bunch of variability, but on average, they had done about 13 years of school. That kind of makes sense. All right, and then another thing that we might want to do is find a residual. We might want to know if the model is over-predicting or under-predicting for a certain point. And the way we find a residual is the observed minus the expected. That's the yi, the real value, minus the yi hat, the predicted value. So let's look at row 21 in this data set. So if I click here and scroll down to row 21, this is a person with one child. They're 34 years old. They completed 15 years of school, so like 3 years of college. We don't have information about how much school their dad went to. Their mom had 17 years of school. Their spouse had 12 years of school, etc. And we might want to find the residual for that person. So first we would need the predicted value for that person. And to predict how many years of school they completed, we'd plug in the highest year of school that their spouse completed, which was 12. So that's what we did in the previous step. I'll just copy that and put that down here. So we predicted that they did 12.975 years of school. And then we're going to do the observed minus the expected. So the observed, that was the real number of years of school that they did. It was 15. So I do 15 minus this predicted value, which was 12.975. So the residual was 2.025. We underpredicted the number of years of school that person had completed. And sometimes it's better to be a negative residual, sometimes it's better to be a positive residual. In this case, I don't know which is better. This person has more schooling than we would expect. Maybe that's a good thing. They went to more school than we thought they would. But that's the idea of residuals, is you do the observed minus the expected, and you look at the outcome. So I think that's all the code you need in order to do the real lab. You could get started on working on that right now, or you could come to our synchronous class and ask me questions.